Alright, so I think I'm recording. Let's take a look at this problem. We've got a third degree polynomial function. They're asking us to find the zeros of this function. And they want me to use the rational zero theorem. So to do that, we look and see that this is written in standard form, that there's no greatest common factor. I look at my constant term, and I want factors of my constant term to be possible denominators in a ratio. So the factors of 3 plus or minus 1 plus or minus 3. Leading coefficient is 2. It has factors plus or minus 1 plus or minus 2. So therefore the list of possible rational, because it doesn't help me with irrational numbers, only rational numbers, ratios of integers, of possible rational zeros. Well, the 1 and 3 are my numerators, so if I divide that by 1, I get 1 and 3. If now I use the denominator of 2, and if I divide by 2, I get 1 half and 3 halves. So there's no guarantee that any of these are zeros of the function, but if this graph does cross the x-axis at a rational number, it'll be one of these values. Doesn't tell me anything about irrational numbers. So let's jump in and do synthetic division and look for a zero remainder. If we find a zero remainder by our factor theorem, then we know that that is an x-intercept, that it's a zero of the function. Alright, so let's try 1. I don't have any missing terms here, so I don't have to put in any zeros. We already said it was in standard form. And so now if I'm just cautious and don't make any silly arithmetic errors, I should be okay. I get lucky, and right off the bat, with the very first one we've tried, we find a zero. That's not always going to happen. Sometimes we may have to try some of these fractions, and I always try those last, but I'm not as fearful of them as some students. So what does this tell me? Well, it tells me that this original this original third degree polynomial function, that using this rational zero theorem, that we can factor this. So by finding this zero remainder, x equals 1 is an x-intercept, and in factored form, we change the sign, because when you plug in 1, 1 minus 1 gives you 0. So now my answer for my synthetic division, 0 was the remainder, 3 is the constant term, 5 is the linear term, and 2 is the quadratic term. So I know this gives me a quadratic equation. So I have the skills to solve this equation now, to find the x-intercepts. To find the x-intercepts, you let y equal 0. So we solve this equation. Now this 2x squared plus 5x plus 3, it does not look to me like this will factor. So I'm going to use the quadratic formula. So let's come up and do it up here. I could be wrong, but when I glance at it, I don't see how to factor it. If I get rational numbers here, then that'll be fine. So it does. Let's identify the opposite of b. Plus or minus b squared minus 4 times a times c, all divided by 2a. So I've got negative 5 plus or minus 4 times 2 is 8, times 3 is 24. That's 1. So hey, it does factor, I just didn't recognize it. The square root of 1 is 1, and if I have negative 5 minus 1, that's a negative 6. And negative 6 over 4 reduces to negative 3 halves. And if I add 1, negative 4 divided by positive 4 is a negative 1. So what I didn't realize is that this guy factors to 2x plus 3 and x minus x plus 1. So I've got 2x squared, 2x, 2 plus 3 is 5, and 3. Yeah, I should have recognized that, but for whatever reason I didn't. So the quadratic formula always works. We're factoring if it doesn't factor, or sometimes, like in this case, when I didn't even take enough time to think it through and see that it did factor, the quadratic formula will still give me the answer. Alright, so it's more time consuming. It would have been quicker if I had just noticed that, how to factor it. Alright, so these are the 3 x-intercepts of a third degree polynomial, so I know I found them all. Now, this original polynomial function, I have ways to factor it. I can see, although I didn't initially see that the quadratic here factored, I do initially see that this factors, I think, by grouping. So if I do have the skills to solve this 2x cubed plus 3x squared minus 2x minus 3. Some people like to put it in the form of a table. Now, most of the time when you're using tables with the x method, you enter your information diagonally, but when you're doing grouping, you just enter it from left to right. So 2x cubed, 3x squared, minus 2x minus 3. If I look here, what's common here is the negative sign. When I look here, the 2 and 3 are relatively prime, but they both, x squared divides both. And if I look here, I have a 2x that's common. So the negative 1 times 2x gives me a negative 2x, and 2x times x squared gives me 2x cubed. If I look vertically here, I have a 3 in common. 3 times x squared gives me 3x squared, and 3 times negative 1, negative 3. So by grouping, well, in this case I really didn't group, I just used a table, but I factor this to 2x plus 3 times x squared minus 1, and then I see that x squared minus 1 factors to x plus 1 times x minus 1, and I have negative 3 halves, negative 1, and positive 1, which is the same answers that I got before. So in this case, I did have the skills to factor it without that rational zero theorem, but this is just confirming my faith and stuff in knowing that this rational zero theorem does work, and it works quite well for cases when sometimes when I can't factor it, when I can't do it by grouping, because for most of these third degree polynomial functions I won't be able to factor them like that. So I hope that helps. I'll talk to you later.